Welcome to the lecture on power series solution. So in this lecture, I am going to discuss about series solution of Legendre's differential equation. So first we will see what is meant by power series method and how to apply the power series method for the differential equation. So consider the ordinary differential equation in the form P naught of x y double dash plus P1 of x y dash plus P2 of x into y is equal to 0. So I am taking an second order ordinary differential equation here. I am going to call it as equation number 1, where this P0 of x, P1 of x and P2 of x are the polynomials in x. That is, all these P0, P1 and P2 are the functions of x. So now to apply the power series solution, we have to satisfy one condition. That is, P0 of x must be not be equal to 0 at x is equal to 0. So if this condition satisfied, we can able to apply the power series method. So now we will see working rule for power series method. So let us assume y is equal to summation r from 0 to infinity a r x power r. So I am taking an equation y like this. So now the given differential equation contains y dash and y double dash. So from the given equation now we have to estimate the value of y dash and y double dash also. So differentiating y with respect to x, I will get y dash. So it will be equal to summation r from 0 to infinity a r I am keeping as it is. Differentiating x power r one time, I will get r into x power r minus 1. So next is y double dash. So differentiating y dash again with respect to x. So again I am keeping the constant summation r from 0 to infinity a r into r I am keeping as it is. Differentiating x power r minus 1, I will get r minus 1 into x power r minus 2. So now replace all these three equations y, y dash and y double dash in the equation number 1. So after replacing these values in the equation number 1, equate the coefficient of various powers of x like x power 0, x power 1, x power 2 till x power r values we have to equate. So in general, when the coefficient of x power r is equated to 0, we obtain the recurrence relation which will help us to find the constants a2, a3, a4, a5 in terms of a0 and a1. So once we equate the general coefficients of x power r to 0, so we can able to find the constants, that is a2, a3, a4, a5 in terms of a0 and a1 I am going to estimate here. So after finding all this constant, we have to replace those constant a2, a3, a4 and so on in the assumed equation, that is y is equal to summation r from 0 to infinity ar into x power r. In that equation we have to replace. So on expanding the equation along with the constants, so we'll get the equation like this. So y is equal to a0 into f of x plus a1 into g of x. So on replacing the constant, if I take a0 common factor and grouping the remaining value as f of x and taking a1 common factor, grouping all the remaining terms as g of x here. So where this f of x and g of x are convergent infinite series in x. So now I'm going to discuss about the actual concept, that is series solution of the Legendre differential equation. So consider the Legendre differential equation of the form 1 minus x square y double dash minus 2x into y dash plus n plus 1 into y is equal to 0. Call it as equation number 1. So this is the Legendre's differential equation of second order. So now in this we have to choose the values of P0, P1 and P2. So here it is clear that the coefficient of y double dash is P0 of x, coefficient of y dash is P1 of x, coefficient of P2 of x is n into n plus 1. So I can choose P0 of x is equal to 1 minus x square, P1 of x is equal to minus 2x, P2 of x is equal to n into n plus 1. So to apply the power series method, we have to satisfy the condition that P0 of x should not be equal to 0 at x is equal to 0. Since we have P0 of x is equal to 1 minus x square, I am going to replace x is equal to 0 here. So I will get P0 of x is equal to 1. That is, P naught of 0 will not be equal to 0 at x is equal to 0. So once this condition is satisfied, we can apply the power series method for the equation. So now assume the y equation. So I'm going to assume y like this. Let us take y is equal to summation r from 0 to infinity a r x power r. Since the given Legendre differential equation contain y dash and y double dash, I'm going to compute y dash, differentiating the given equation with respect to x, and I'm going to compute y double dash also, differentiating the given equation with respect to x twice. So I will get y dash and y double dash there. So we'll see, after differentiation I'll get the equation like this. So y dash will be equal to summation r from 0 to infinity ar x power ar into r x power r minus 1. Y double dash will be summation r from 0 to infinity ar r minus 1 x power r minus 2. So now replace all this equation y dash and y double dash in the given Legendre's differential equation. I will get the equation like 1 minus x square. So I'm keeping 1 minus x square as it is, replacing y double dash as this equation, that is summation r from 0 to infinity ar r minus 1 x power r minus 2 minus keeping 2x as it is, replacing y dash as summation r from 0 to infinity ar x power r minus 1 plus n into n plus 1 into summation r from 0 to infinity ar x power r is equal to 0. So now on simplifying this equation, so if I multiply 1 with this equation, I will get summation r from 0 to infinity r minus 1 x power r minus 2, I will get it. If I multiply x square with the summation equation, I will get the equation like minus summation r from 0 to infinity r minus 1 x power r, and again in the next term multiplying x with the summation, I will get minus of summation r from 0 to infinity 2 times of r x power r plus n into n plus 1 summation r from 0 to infinity ar x power r is equal to 0. I am keeping as it is. So I am going to group the all equation. So I am taking all x power r term common factor, taking ar summation x power r outside. So grouping the remaining term, I will get the equation like this. And so after grouping the term, I am going to equate the coefficients of x to 0 first. So in the previous equation, if I replace the coefficient of x to 0, so I will get x power minus 2 coefficients only I will get it. That is, I will get a naught into 0 minus 1 is equal to 0. So this equation is obtained when if we replace r is equal to 0 in the previous equation, I can able to find the value of x power minus 2. So it will be equal to a naught into 0 minus 1 will be equal to 0. So I can get a naught is not equal to 0. So if I take the coefficient of x power minus 1 coefficients, so I will get a1 1 into 0 will be equal to 0. So a1 cannot be 0. So I will take a1 is not equal to 0 here. So if I take the coefficient of x power r, so I will get ar plus 2 r plus 1 minus ar into r minus 1 minus 2 times of r plus n into n plus 1 ar is equal to 0. So I am going to express ar plus 2 in terms of the remaining equation. So I will get the equation like ar plus 2 is equal to minus of n into n plus 1 minus r square minus r divided by r plus 1 into r plus 2 into ar. So now from this equation, I am going to estimate the next constants, that is a2, a3, a4, a5 and so on. So now in that equation, let me replace the values of r like this. So if I replace r is equal to 0, 1, 2, 3, we can able to find the next further constants. Suppose if I replace r is equal to 0 in the previous equation, in ar plus 2 equation, I will get the equation like a2 is equal to minus n plus 1 by 2 into a naught. If I replace r is equal to 1 in the previous equation, I will get a3 is equal to minus of n minus 1 n plus 2 by 6 into a1. If I replace r is equal to 2, I will get n into n plus 1, n minus 1, n plus 3 by 24 into a naught. So, and also again by replacing a r is equal to 3, I will be able to find a phi is equal to n minus 1, n plus 2, n minus 3, n plus 4 by 120 into a1 and so on. So now I'm going to replace all these constants in the y equation. So first let me expand the summation y. So y is equal to, I will get a naught a1x plus a2x square plus a3x cube plus a power 4 x power 4 and so on. So if I replace all the constants like a2, a3, a4 in the equation and taking the common factor of all a naught and all a1, grouping all the remaining term in one side. So I will get the equation like y is equal to a naught by replacing all this as u of x and a1 and grouping all these terms as v of x. So where this u of x and v of x is an infinite series, yeah, see here it is an obviously an infinite series here, and this series solution, and this is a series of solution for the Legendre's differential equation. In the next lecture, I am going to discuss about the Legendre's polynomial. Thank you.